Okay, good morning to everyone. It is a great pleasure for us to be here in this last seminar of the year. In this opportunity, we have our closure invited talk, which will be given by Valdemar Macedo from the Centro de Desenvolvimiento de Tecnología Nuclear in Belo Horizonte, Brazil. And in this opportunity, he will talk about investigation on interfacial effects in iron-based layered magnetic structure. Okay, and before starting, a few words of our speaker today. Valdemar obtained his PhD in physics from the University of Duisburg in Germany. Also a master and specialist is a master and specialist in nuclear technical science from the Federal University of Minas Gerais. He obtained his bachelor degrees in physics from the State University of Campinas. Then, a few years later, he was a visiting researcher at the University of California in San Diego in the United States. He's a full researcher at the CEMN, a permanent professor, in the postgraduate course at the CEMN also, and he obtained a scholarship of the Minas Gerais research program from FAPEMI. From 2014 to 2018, he was appointed director of the CDTN, or of the Centro de Desenvolvimiento de Tecnología Nuclear. And he has experience in the areas of experimental condensed matter, physics, and material science. And his main working topics are Mössbauer spectroscopy, nanostructure magnetic materials, thin films, and ultra thin films. And among other surface physics, metal alloys, and nanoscience and nanotechnology. With this being said, I will leave Valdemar sharing my screen, so Valdemar can start his presentation whenever he thinks is okay.
Thank you very much, Luis, for the kind invitation, and thank you, Carlos, and you all for inviting me for this series of seminar. It is a great pleasure for me to talk for you guys, and let me start sharing my screen. Okay. I hope you can see it.
Yes, it's in full screen now.
Okay, great. Perfect. Okay, I'm showing you, you see, we have some collaborations, casual collaborations with Bariloche, with you guys, with Roberto, Zizer, and Carlos, and Elin during last years, but we never succeeded to get a formal collaboration or regular collaboration. I hope that it's still time for the young guys to do that in the next years. Let's see. Oh, this is not working. I wanted to show you where Belo Horizonte is, but I hope you know already. But Belo Horizonte is very close to Ouro Preto. It's a nice city. Belo Horizonte is a big town, but is only 1 hour drive from Ouro Preto, a very nice place. You should come to Belo Horizonte. But inside Belo Horizonte, CDTN is, in fact, it was grounded by the university, Federal University of Minas Gerais in the 50s, and was taken from the university during the military government in the 70s. And since '88, we belong to the National Nuclear Energy Commission, belong to the Ministry of Science and Technology. And okay, as any, you know very well, as any nuclear research center, we are very multidisciplinary. We have different areas of work in our institutions. And we belong to different national institutes of science and technology that's in the SLS networks in the country, and 2 of them are in magnetic materials. And we have also, okay, my lab is just in this building. We can see the stadium, Mineirão here. Okay, this is the high part of the campus. This is the lower part of the campus. Here is the reactor that was the starting point of the campus outside of the town at that time in the 50s. And okay, thing that I wanted to point out is that we have also, since 2002, a graduate program. It's a multidisciplinary program, and it's a good program. Because say we have a level 5 in our CAPES now, Ministry of Science of Education. Is a good program, but very multidisciplinary program, a small program with 100 students and only 30 professors. Okay, I'm one of them. Okay, we have also, like in Bariloche, we have also a unit for producing radiopharmaceuticals. We deliver every morning for radiopharmaceuticals of fluor-based FDG, for example, for clinics and hospitals. That means we are a complex institution like in Bariloche. You are in Bariloche. Okay, in my lab, in the Laboratory of Applied Physics, we do surface physics, Mössbauer spectroscopy, and a lot of nanomagnetism. I think we have 3 different legs in the lab. And today I want to talk about, let's say, magnetic nanostructures and thin films, okay? And to do also a lot of work on XPS based in collaboration with internal groups, doing materials for bio applications, and also from external groups. And you do also a lot of regular analysis of by Mössbauer spectroscopy and magnetism, magnetometry, for, let's say, conventional materials, so no nanomaterial, okay? And the importance of the material that I want to talk about today is, of course, we have here 3 reviews that are from a few years ago, but very up to date, showing the importance of magnetic multilayers or magnetic systems based on thin films, where you have a lot of important effects for spintronics and many other new technologies and new effects based on interface-related phenomena, okay? And of course, in all these systems, you always have to have one pinned layer, and in this context, exchange bias, that means the coupling between ferromagnetic and ferromagnetic film or interface is still very important and not fully understood, okay? And in all these, let's say, layered systems, you have many issues that is still not very well understood and very open questions. And we always need access to buried interfaces, and would be very good to have, let's say, site-selective measurements. And how do we do that? That means we don't have many techniques for that, but for example, we can do XMCD, or X-ray absorption, where you have element specific. You can select different materials, but the depth resolution is not that great. We cannot go below, let's say, 4 nanometers deep. And the other way to access the information in the selective way is doing isotope-selective measurements like Mössbauer spectroscopy or nuclear resonance scattering of synchron radiation, where you can study specific sites within the same material, same element, and you can, with resolution of few angstroms, you can go up to, let's say, 300 nanometers deep inside the materials. And this will be the focus of my talk, part of my talk today. That means this is the outline of my talk. I will give you a few words about a very short introduction on Mössbauer important aspect of Mössbauer spectroscopy, and then you talk about exchange bias systems, the depth selective measurements in exchange bias systems, FIF bilayers, about interdiffusion, also magnetic anisotropy and induced magnetism in epitaxial iron cobalt films on a non-magnetic substrate prepared by molecular beam epitaxy. Okay, about Mössbauer spectroscopy, this is okay when you have the Mössbauer effect. You, of course, it's a gamma resonance, but in the decay after excitation, you can have electrons, X-rays, or gamma produced from the decay of the iron 57, and you can, let's say, you can detect X-rays, gamma rays, or electrons. And if your sample is not homogeneous, you can have different. That means you have different. You can probe different depth inside your material. That means if you are detecting electrons, you can say that conventional electron Mössbauer spectroscopy is a surface sensitive technique, but surface means 2000 nanometers also, okay? If you can, let's say, detect these electrons that are coming out of the material after the gamma ray absorption, the resonant absorption, but you can use an electron analyzer to select the energy of the electrons. You can have some electron depth selectivity doing that. And this selectivity is not bigger than 100 angstroms, okay? Because of the energy of the electron. That means this is doing this, what we call depth selective conventional electron Mössbauer spectroscopy. This CEMS, it is very interesting for doing, let's say, material science with this kind of, you can, let's say, in a book material, you can, by selecting the energy of the electron, you can have probe different depths inside your materials with this 100 angstroms selectivity, but it's very interesting for, let's say, for 6 samples, for material science, for coatings, things like that, or IO implantations, but it's not enough for nano, okay? If you want to go really nano, one way to do that is to play with the isotopes. That means you know that the Mössbauer isotope in iron is iron 57. It's only 2% of the iron, natural iron, okay? And if we can play with these isotopes during the preparation of the samples, you can be very, very depth selective. You can go to the monolayer regime inside the materials, okay, if you are able to play with the isotopes. If you use the iron 57, you are fully Mössbauer atoms, and the iron 56, for example, is you don't get any Mössbauer signal from these things, okay? That means using this iron 57 probe layer is a very effective method to investigate layered materials based on iron, for example. And that means then you don't need a big analyzer like this, or what this is an analyzer I have constructed in Germany few years ago. You see, I still had the hairs at that time. But you can use, let's say, a very simple homemade gas counter. You can be sensitive to, let's say, this is a spectrum of 2 monolayers iron 57 or 4 monolayers iron cobalt alloy. And another important thing when you do Mössbauer spectroscopy is that from the line intensity ratio between the lines 2 and 3, you can know about the texture of the iron spins, okay? That means this line is for a random distribution. We have this line 2 and 3, the ratio is 2. When the spins are parallel to the gamma rays, this line 2 disappears, the ratio is 0. And when the spins are perpendicular to the gamma rays, this ratio is 4. But in this case, you are not sensitive to the spins in one direction or in the perpendicular direction. But if you can go to, let's say, a non-perpendicular geometry of the incidence of the gamma rays, in this case, you are sensitive to rotation of the iron spins in the sample plane, okay? And this is what important for the things I will show you today. Okay. In our lab, what we do in nanomagnetism, I've been studying, let's say, the correlations between structure and magnetism, how the epitaxy, how the, let's say, when you do epitaxy, you can play with the strain or the lattice parameter of the materials, how it changes the magnetism of different systems, studying also exchange bias, and right now we are still interested in nanostructures of Heuser's alloys based on iron cobalt to iron. And always when possible, we use the iron 57 probe layers approach and simple radiation to investigate our systems. Okay, based on that, these are the systems we have in our lab. We have a lot of equipment to grow films and surface and do surface physics and preparation of samples. And you can prepare iron with samples with iron 57 by molecular epitaxy in these systems, or even by sputtering in this another system, okay? And then this is where the same system where we play with iron 57 in the samples. We can get very nice epitaxy in different systems. And this is an example of very nice layer by layer growth, but a system that we don't have iron in this case, you cannot use Mössbauer spectroscopy here. But let me go to the results I want to show you today. For the exchange bias systems, one of the systems we have been studying years ago was the iron fluorides, and we have basically prepared samples doing the placing the iron 57 at different distance from the antiferromagnetic interface, and this shows that in these samples you have fully in plane spins. That means if you want to see something, you have to go to non-perpendicular geometry, and this is what we did in this case. But we see that these measurements were done in remanence. That means what we have seen is that as long as you have the order of the antiferromagnetic laser, that means you go below the nail temperature of the iron fluoride, you will see that the lines intensity in this Mössbauer spectra change. That means we are proving that we have in-plane spin rotations in these samples, but it is in remanence. And another thing that after that we got beam time at the synchrotron in Grenoble in the Mössbauer line, say for doing nuclear resonance scattering, and we have prepared a sample like this with let's say just one diagonal of iron 57 in the same systems, and that means you have also again fully in plane magnetization. The samples are very sharp interface, and with nuclear resonance scattering, the same as Mössbauer, you do the measurements in time domain, but from the spectra you can get the same information regarding the orientation of the iron spins. Okay, it's equivalent to the Mössbauer spectra, to the normal Mössbauer spectra, and for that, by using the, let's say, the small size of the synchrotron beam, we could, let's say, move the sample in front of the beam, doing along all the threads loops of the system, and then we were able to, let's say, to see that the magnetization reversal is dependent of the depth. That means the pinning of the iron is much stronger, closer to the interface when you compare to another point that is more away of the interface, the center of the sample. This is a clear sign of the stronger pinning closer to the interface, and the rotation is like a spring magnet. Okay, and you see also that the reversal below the nail temperature is, you have here, let's say, this jump of the spins from one direction to the other direction of the antiferromagnetic spins of the fluoride. And you see this jump below the nail temperature, but you don't see this jump above the nail temperature. That means really a signature of the spins of the antiferromagnetic material is playing an important role in these samples. And then we decide to do, it's not easy to get beam time in the synchrotron for doing Mössbauer. We decided to investigate another system where you can do at home the similar approach. What we did is we have investigated the iron manganese as antiferromagnetic. This is antiferromagnetic at room temperature. And then we have prepared different samples by sputtering, placing the iron 57 at different positions regarding the antiferromagnetic iron manganese phase. And then we did conventional electron Mössbauer spectroscopy. Okay, what was very difficult in this system was to get the equivalent samples, because the preparation is not very trivial, but to get equivalent samples to be able to prepare was really a nightmare. And then after getting samples prepared by sputtering with iron 57 different layers, we could then go to do Mössbauer. We see that the normal Mössbauer shows that these samples are fully in plane, and then you have to go outside for the non-perpendicular geometry to be sensitive to in-plane rotation. And then doing that, we have a prepare, you can do the Mössbauer spectra, apply magnetic field, and from this R23, or for the line intensity ratios, you can construct hysteresis loops for the iron spin rotation, then this is what we get. We see that the blue line is the, let's say, the average of the sample, the loop from VSM, and the red one is the Mössbauer hysteresis, okay, from one position of the iron 57 layer, okay? But if we compare then the different loops for the iron layers at different distance from the interface, we see that the reversal, when you go from from positive to negative, you see that the reversal is very different. You have a stronger pinning at the interface, and the average represents the BSM loop, and on the top is much easier to rotate the iron 57 layer than the average of the sample, okay? But when you come back, you see that the reversal is always the same. That means you see a clear sign of the asymmetrical reversal. We have one kind of reversal when you are going from positive to negative. You have an exchange spring-like magnetization reversal. And you see that when you go from negative to positive, you have a reversal by coherent rotation of the whole ferromagnetic layer. Okay, and this is important for the theories of exchange bias. Another thing that we have been studying that is important in this system was interdiffusion as this interface. You see that the behavior for, let's say, for device, for example, can be very important to know how the interface behaves. We have been testing the cobalt iron iridium manganese interface. That is a very, let's say, model system for industrial application of exchange bias. And we have seen that for this system, when you do the magnetic annealing to improve the exchange bias, you will see until 450 degrees, you have a small, this central peak is a sign of interdiffusion in the system. And you see that at 500 degrees, you have a strong interdiffusion, okay? And you see that although you have still a very significant exchange bias, the diffusion is really high at above 450 centigrades, and the exchange bias is maximum at this temperature. And you see also that doing XPS, that the manganese diffuse all the way through this stack and appears at the very surface, top surface of this stack. Okay, and like you see here, that manganese is going through the whole stack. And what you can say is that our results is very different from you get from different groups. And what you can say is that the magnetism of and the structure of the interface for this system is very dependent on the processing parameters. You have been studying also more recently the manganese systems, films of manganese to gold. It is a very important system nowadays for antiferromagnetic spintronics because you have a very high Nell temperature and a strong spin-optic coupling. And you have been growing films of this system by sputtering. And the only way for us to know if you have really antiferromagnetic manganese to gold was to probe exchange bias in these systems. And though we did that, and these systems were used in these works, and if you go to the literature, you see that manganese to gold is a very important material nowadays. And the only thing I want to show you today is that by doing the same experiments, putting a layer of iron 57 at the interface between cobalt to iron and manganese to gold, we see that this system is much more stable than, is more resistant to the diffusion than iridium manganese cobalt. You see that at 500 centigrades, we still have, let's say, a strong ferromagnetic spectra, much more robust than more robust than iridium manganese. Let me change now for epitaxial system. Magnetic and the perpendicular magnetic and anisotropy is very important, for different applications, for memory, for device. And the orthogonal distortions play a very important role in the induction of perpendicular magnetic anisotropy. And the iron cobalt on rhodium is a model system. And people have shown that by doing MOC measurements, that for this system, you can get, doing polar MOC, you can get, let's say, square loops until 15 monolayers. And you have probed the system by doing iron 57 and conventional electron Mössbauer spectroscopy to map the spin texture and to determine how sharp is this iron cobalt rhodium interface. And then what we have done is we have put in a always 12 monolayer stack, we put 4 monolayers of iron 57 cobalt at different places of this regarding the interface. And we did lead to see that the system is epitaxial. We did the Auger to prove that it's 50-50 equiatomic. And you do longitudinal MOC, you see that this looping longitudinal geometry is not square. That means the magnetization is not in plane. And if you do Mössbauer, what we see is that if you put iron 57 at the very interface, you see that this blue spectrum does not show lines here. That means the spin at the very interface is really perpendicular. But if you go 5 monolayers away from the interface, we start to see some blue lines here, near the lines 2 and 5. That means you have some spin canting. Okay, we start to lose the perpendicular the really perpendicular orientation of the various spins, and we believe that this is because of the growth. That means after, let's say, above 5 monolayers, we start to lose the layer by layer growth. We start to see some island, and I believe that this island has been responsible for this some spin canting that we observe. But for the iron cobalt, there is also, we went further with the system, and based on this theoretical work that says not only tetragonal distortion, but also the chemical order should have influence on the perpendicular anisotropy. And these calculations points out that copper 3 gold would be, if you could have ordered iron cobalt, L10, that means on. Tá? Você pode botar para mim a extensão que eu não tenho energia. Hã? Lá tá? Você pode colocar para mim, por favor. Okay, excuse me, they are losing the problem with the energy here. Tanto faz. Obrigado. Okay, now you have a battery for the whole talk. Okay, and okay, based on this calculation that the chemical order could also favor the perpendicular magnetic anisotropy in the system, these guys did the only experimental work that we know. They tried to, they have grown alternate monolayers, single monolayers of iron cobalt. That means to make an ordered stack of iron cobalt on top of copper 3 gold. But they didn't see plane magnetization for 11 monolayers. But they claim that they speculated that below 9 monolayers, they should have been, we should observe perpendicular anisotropy. And what we did is that we have grown then alternate iron cobalt monolayers on copper 3 gold, always 1 monolayer iron, 1 monolayer cobalt, and so on. And we did the growth. Then this is here the results. We did the growth by molecular epitaxy. You see by reading that you have really the lattice parameter is the same as the copper 3 gold substrate. You have a layer by layer growth. And you have compared the, let's say, the alternate iron cobalt monolayers with co-deposition of iron cobalt on the same copper 3 gold substrate. We see that from the structural point of view, they are equivalent. And let's see what happens with the magnetism. Let me show this slide. what we have now is that by doing polar MOC, you will see that for 3 monolayers, we have, let's say, perpendicular spins. For 4 monolayers, you have in plane. For 5 monolayers, you have perpendicular. For 6 monolayers, in plane. That means you have an alternation of the spins with the deposition of 1 monolayer of iron or cobalt, depending on the top layer, okay? And if you compare with co-deposition, you see that for co-deposition, you always have in-plane magnetization. That means we really have shown that the chemical order matters for the anisotropy of iron for ordered iron cobalt on top of the copper 3 gold. That means, but we are not able to do 1 monolayer iron 57 resolved Mössbauer spectroscopy in this system because we are not sensitive to just 1 monolayer. For that, we would need synchronous radiation, okay? Mössbauer to a much more intensity for that. But we tried to do the same experiments in the synchrotron. We went to Campinas, and we wanted to see this same behavior, this the reorientation depending on the top layer of the system with the XMCD, but because of, let's say, contamination of the system was not, we have grown the samples by MBE, but we have to go through a, let's say, to not so clean system to get to the measurement chamber, and we didn't get this alternation of the spins in the system. But what you have seen that there, of course, XMCD is element specific, but we don't have any depth resolution in these measurements. But what was interesting that you have seen that copper, that means the non-magnetic substrate gets magnetic. That you see XMCD signal from the copper in the copper atoms, and these are the guys that did this work. And then we just want to show them. We forget that Sofia is now in Spain, Rodrigo is now in Germany. That means we're having a very strong problem with personnel in Brazil right now. A lot of people live in the country to do science outside Brazil, but it's really a pity. But okay, we didn't do the depth resolution measurements because XMCD is not depth resolved, but the theoreticians got interested in this system, and they did the calculations by DFT, and they did all the, let's say, the epitaxial growth, theoretical growth of the system by up initial spin polarized calculations, and they have shown that they did the layer resolved calculations, and they have shown that this induced the magnetic moment at the interface is due to the broadening of the density of states because of the first iron cobalt bilayer at the interface of the substrate, and they did the calculations and you did also the experiments for stacks starting with iron or starting with cobalt at the interface, at the very interface. And what they have shown was that this magnetic induction, that means this dichroism that I've seen in the cobalt, in the copper atoms, are a very important point for this system is that let me come back. A very important point is that for the copper 3 gold 100, we have that it's an ordered phase, and we have always planes that you have 50-50, that means 50% copper, 50% gold, and then one plane that is pure copper. That means the first layer is 50-50, the second layer is copper, the third layer is 50-50, and so on. And what they have shown here, this calculation, is that only the first 50-50 monolayer is magnetic. That means that this induction that we have seen is only at the very interface atoms. That means, and the third layer where the copper, you have copper again, are not magnetic at all. That means only the very first copper 50, gold 50 layer of the non-magnetic order, the copper 3 gold substrate, is magnetic. That means showing in another way, we did also we have applied some rules. We have calculated the magnetic moment, the spins and orbital moments extracted from XMCD experiments, and we have compared it with the theoretical calculations. We see that the numbers are very reasonable. The experiments with the theory are very good agreement, and this is another way to see the theoretical results. We see that the spin moments we have measured in copper are due to the very first layer of the ordered substrate, and we should have also magnetic induction in the gold atoms, but we cannot measure we are not able to measure in the old synchrotron that we did when we did the measurement, okay? That means the XMCD measurements we have observed are due to only half a monolayer of magnetic copper atoms, okay? And this is very important. That means that we were able to get the depth resolution from the theoretical calculation, what is very, very, very nice. And okay, I want to summarize this part. I want to try to, I was a little bit too fast, but I want to summarize to say that the correlation between structure and magnetism can be very complex, and a good understanding of these different systems is a non-trivial task. And we always need a multi-technique approach to understand different systems. And using iron 57 in Mössbauer spectroscopy can be very interesting for the investigation of iron-based magnetic nanostructures. And since we don't have any theoretical group in our institute, the collaboration of the theoretician is always very important, very welcome. What is not, I was very happy with the collaboration with the theoreticians from the Unicamp for this system. I was running with this thing because I want to show you a little bit more what we could do with this similar approach by using synchronous radiation or I want to show you here a few results. This is a very nice paper work done at the Mössbauer line at Spring 8 in Japan by Mitsui, and they have measured 2 years ago this Friedel oscillations at the iron one surface. And these oscillations were predicted 40 years ago, and only now there was being this paper from 81, and they have shown that because of the broken symmetry of the iron surface, we should observe an increase of the magnetic moment at the free surface of the iron, and decrease of the hyperfine field of the iron atoms. Okay, and what they did in these experiments is they used this synchrotron Mössbauer source, and you can get 10 to 5 more counts now or more intensity than a conventional 100 millicurie, very strong Mössbauer conventional cobalt source for Mössbauer spectroscopy. That is what we use in our lab. And okay, but what they did, they have grown just one monolayer of iron 57 in iron 56 film, epitaxial film, at different positions, okay, at the interface or going down with until the 7th layer of the iron of the iron. And what you have seen is that is a decrease of the hyperfine field at the very surface, and then an increase at second layer, and so on. And from the first layer, starting from the first layer, the spectra are book-like. That means at what they have seen is that the hyperfine field oscillates, in a layer by layer fashion, and they explain this is due to the increase of the magnetic moment as foreseen as should be. Okay, this means the first evidence that you have by doing iron 57 atomic layer resolved Mössbauer spectroscopy with the synchrotron. Okay, doing in this Grace incidence geometry in the spring 8, they are able to finally show that there is really Friedel oscillations at the surface of the iron 57, of the iron 001 surface. That is what you can do nowadays by using this approach. I want to show you one more result for that. Now is from the results from the same beam line you have used years ago to do nuclear scattering. They are now they are able to do, let's say, conventional Mössbauer in the velocity domain, the energy domain. And this work is investigation of the yttrium iron oxides. Okay, this yttrium iron orthoferrite is a very interesting material for antiferromagnetic spintronics. Okay, and what they have done is they have grown a wedge sample of iron 57 with thickness varying from 3 to 14 nanometers in this 10 millimeters long wedge, and they did this with the same setup. They were able to do the Mössbauer spectroscopy with, let's say, a lateral resolution of 11 microns. Okay, and what they got is this. Okay, we have seen that for a film that is only 6 nanometers thick, you see this kind of spectrum. That means, and if you measure in another point, okay, of some millimeters away, that is 27 millimeters thick, for example, this point and this point, if you compare both, you see that the line intensity ratio is totally different. That means what you are measuring, what you are seeing is a depth or thickness dependent spin orientation, okay, in the material. Okay, that means the orientation of this of the antiferromagnetic axis of this orthoferrite depends on the film thickness. And this is very important for this potential application of this material for antiferromagnetic spintronics. Okay, and this is really, I consider this really a very, very interesting result. And with that, what I want to do is I use that to say that we hope, I hope that we will be able to have in our new synchrotron at the Sirius, at the second phase of Sirius that is they are planning now to construct along the next 4 years. We hope to have a line for nuclear resonance scattering or for synchrotron Mössbauer source to be able to do Mössbauer spectroscopy in a very with pushing the limit in the Mössbauer spectroscopy using isotope probes. That will be really very important for not only for magnetism or non-magnetism, for many, many areas of science. Okay, and just to finish what we are doing now, we are growing nanostructures of iron Heuser alloys based on cobalt-2 iron, and we are comparing, let's say, nanowires grown by wet chemistry with thin films grown by sputtering, because these materials it's not that easy. The magnetic properties of the Heuser alloys depend very much on the chemical order of the materials. I forgot to put a slide here, but it's not that easy to get the Heuser alloys in the nano regime. Okay, and we are doing by using this silica template. We can, let's say, you can induce the growth of wires in the, let's say, in the walls in this mesoporous silica, and also internal channels. And we did a lot of work during the pandemic with that. But we started growing this kind of materials. We see that we got nanowires induced by the silica, mesoporous silica, and then we remove the silica, we get the metallic wires. You see that we have, let's say, we didn't do a lot of, we see some deviation in the stoichiometry. We didn't do much analysis because of the pandemic in the materials, but if you do X-ray diffraction, it seems that you have really the nice, the good order led to Li2-1 or B2 phase of the cobalt iron gallium Heuser alloys. Our idea was we wanted to, let's say, to isolate just one single nanowire to do transport measurements in this kind of, let's say, electrode, but prepared by lithography. But after doing the Mössbauer spectra, in fact, they realized that we have a lot of alpha iron in this material. And then if you use the information gained by Mössbauer spectroscopy, and if you redo the X-ray analysis again, you know that you will see that you get equivalent fits by considering 50-50 cobalt-2 gallium plus iron alpha iron. That means it's almost impossible to separe alpha iron from this alloy, from this phase, from the conventional X-ray diffraction. But that means Mössbauer spectroscopy is very important for the characterization of these materials. But if you do ultra-thin films, you can get very, very nice, very ordered, the single phase cobalt-2 iron gallium. And just to finish, to make you happy, I want to show you that we are just starting to do ferromagnetic resonance measurements with collaboration with Klaus Kronbach in the physics department. This is from this week, and I still do not know what to do with that, but we want to use magnetic resonance to determine the damping in these materials. Okay, and with that, I want to thank my many collaborators along these many years in these topics, and my collaborators in my group and in Brazil with the last results I have shown you. And I want to thank you all for the attention. Thank you.
Thank you, Waldemar. Everyone is clapping in the conference room. Thank you for the nice talk. I would like to open the session to questions. I have 2 or 3 questions, but if
apologize, I hope I was not too fast.
It's good. So I think Elin has a question, no? Probably. No, okay. But I can start if you want. So I realized that you have a very sensitive technique to the interfaces. However, what's happening when you fabricate samples with sputtering? You fabricate samples with sputtering, and you are losing crystallinity as you are away from the substrate.
Not really. Depends how do you prepare. Okay. You can get very, very nice, very epitaxial, very nice samples even by sputtering. Depends on how do you prepare. This is it.
Okay, but for example, when you have a multi-layer and you fabricate your iron layers on top of iron manganese or iron,
Yeah.
the growth is not going to be the same, isn't it?
Oh yeah, that was let's say this is what I said, because it took us years to be able to get equivalent samples, because we don't use the same target. That means we use a very small target, 457,
Yeah.
at very different distance. The energetics is totally different.
Okay.
Okay. And it took us really long to learn how to get samples that are really equivalent to the standard growth we use it to do samples without the set.
Okay, I understand. Okay, thank you.
But we do let's say cross-section transmission, cross-section electron microscopy. Okay.
Okay.
To see how it looks like.
Okay, I have another question about the proximity effect in the samples grown on
Yes.
copper gold.
Yeah.
So you show with the simulation that you can induce a magnetic moment on the copper by depositing a monolayer of cobalt, a monolayer of iron.
Yeah,
but
you have a proximity effect only at the very first layer of
yes,
the substrate.
Yes. But did you try with the alloy? What happens if you do not have a pure layer of cobalt, but you have the alloy on top of the copper gold?
You know, we did we have the calculations for I stack starting with iron at the very interface, or starting with cobalt at the very interface.
Yeah.
Okay. The values, that means if you have the mixes with the same, you have you see that the moments change a little bit. Okay. You have
yes.
A little bit different moments, but not very, very significant.
Okay.
But we have all the numbers in these papers. We have all the numbers. If I can, should I go back?
No, I think it's okay. Yeah. And
okay, I can show you the numbers. But
okay.
We have the numbers for integrations. Okay.
Then I think I had another question.
What is very interesting in this calculation is that you have a, let's say, a big orbital moment.
Okay.
But let's say that we still should measure that means now in the series, the new line in the EMA-beam line, at Sirius, you can measure the border of gold. It means we can repeat the system now. We can go to the gold border edge, and we can go to the gold edge and measure XMCD in the gold atoms.
Okay.
And then have the calculation.
Okay. Then yeah, I am interested in the iron cobalt samples, because this is an alloy that has interesting properties also in the damping. Depending on the crystalline structure, you can have an isotropic damping, and in this case, maybe one can correlate this phenomena with the substrate that you use to fabricate your sample. But probably that's a discussion for another moment.
Yeah, okay. We'll be happy to do that, to do something.
Yeah.
Together.
Yeah, for sure. I would love to. Is there any other question?
Just a comment from this place. Thank you very much, Valdemar. I think I got about 5% of all the things that you said. You comment many things, and I'm surprised by the capability of Mössbauer to see all these things. So Mössbauer is going to be associated with light sources, you said, in the future.
No, not going. It is already. Nowadays, you have
It is
a
already.
lot of work on the lights. That means you have to go to light
No.
sources for Mössbauer. Now you have, let's say, even doing Mössbauer images, okay? Now we start to go the nano, okay, with nano result, with, let's say, with very good, let's say, tens of nanometers resolution for even for images, I think. Okay, that means it's still very powerful. It is still very, let's say, up to date. So you have to go to let's say, synchrotron-based Mössbauer, and then you can go to many other isotopes, not only for iron. Okay, you have, and you spend a lot of your. Okay, that is a new world. See, and people are doing a lot in France, in Japan, in Germany, in the US, and many others. That means in the fourth generation machines. Okay, that means.
Yes. Okay. But
and this is very, I would say, is a very important, very good opportunity for Latin America, because a lot of Mössbauer groups, okay, around, and we should get support for all the community to, let's say, to make pressure to the guys at Sirius, to the LNLS, to really to go for a beamline for Mössbauer. For resonance scattering. Okay, that is my point. Okay.
Voy a cambiar a castellano.
We have to convince students or young guys to get involved with these things abroad, okay, everywhere. To go to the Mössbauer groups in the synchrotrons in Germany, or in Hamburg, or in Grenoble, in Japan, or Argonne. They should go. It must go. That means we have to convince young people to get experience on that, and then they could come back and use, okay, or to, let's say, to collaborate and support the guys in Campinas and let's say at home, okay. But my point is that we need young guys involved with these things abroad, okay. This is the point. It's powerful not only for nanomagnetism, for for soil, for earth sciences, for many things, for bio, okay.
Okay. Now, una de las cosas que tenía Mössbauer es el pequeño ancho de línea que da la transición nuclear. Eso se mantiene en synchrotron.
You have a trick, okay? You have a trick to do that. You have to use a single crystal. You use the Mössbauer transition to get this, okay? You shine a sample that with let's say a very broad synchrotron line, okay? And then you do Mössbauer effect, and then you get this is the emission for your sample, okay?
Okay.
I didn't stop, but I can, let's say...
Otra pregunta que tengo.
Sí.
Bueno, how did you manage to do a layer by layer growth? What do you use, the MBE or sputtering, or
MBE,
what are the conditions?
MBE. Layer by layer, we use MBE, yes.
Because the growth also, it's very difficult to get layer by layer.
No, this is why I lose my pillows. You are growing samples, epitaxial samples. It's really. But we know how to grow good samples. This is.
Tenemos que ir ahí para.
You have to prove that the sample is as good as you wanted to have. Okay, because many times the sample I have in mind is this, but you do not prove that the sample is the nominal sample you wanted to have. Okay, but we manage that. We can. It is possible to grow very good samples.
Okay.
Put your
now the MBE you have is specific for metals, for magnetic samples, or
metals. I have MBE for metals. Okay.
Yeah. We could have that here. They are specific for 3.5. I don't know. We got an LBE, but
No,
well,
my system
thank
is
you very
only for
Valdemar.
what we do is we play with metals. We have up to 10
Okay.
metals inside with small pockets,
Okay.
and we can combine any really big Mac with metal.
Oh, nice.
Or by sputtering, we can do oxides or things like that, but we don't do semiconductors, okay? Sometimes we get semiconductors grown, for example, in France by Victor, then we can, let's say, take the sample that is protected, we remove some protection, and we grow again. We start growing on top of semiconductor, something like that. But we only have metals in our system.
Well, many topics, too many for me.
No, the idea was
Thank you very much.
It means you can do is something that we should find a way to finally to work together. Or the CONEAS labs.
Well, ferromagnetic resonance we have here.
Yeah, good.
And a link can tell you about that. We are doing that, and we are seeing.
That you have to start having people, let's say, moving, back and forth.
Okay,
we have
that would be nice.
To really be that connection, to have a beer together and sit down and say, okay, let's do that. It's not that expensive. I think money for that we have, okay? For short visits, only in Belo Horizonte, you can go to Ouro Preto, have a beer, and then you combine what to do, or spend 1 week in Bariloche having a wine, okay? But this is a journey. We should start working together. That means, and what is missing is the personal connection, or let's say the short visits. So this is what is missing.
Okay.
Okay, and then very open. I will be very welcome if someone want to come to see what we can do, because we are right now. I'm getting almost, let's say, I'm getting too old. My time to let the young guys run in the lab.
The business. Okay.
Yeah.
Thank you very much, Valdemar.
Thank you, Valdemar. Thank you for your very nice talk and for closing our seminar series of this year. With this, I would like to stop recording, and thank you all for being here. See you next year.
Okay, thank you all for the invitation. Bye-bye.
Bye.